Hi there, this video is going to walk through the exercises using the harmonic oscillator wave functions. So the first one we're going to start with is actually putting together a couple of harmonic oscillator wave functions from the equations that were given. So here is the total harmonic oscillator wave function. Remember, that's a product of a normalization constant, which is given by the expression over here. Your Hermite polynomial, remember that's a function of alpha to the 1/2 x, not multiplying by alpha to the 1/2 x. Those are given over here in our table of Hermite polynomials. You should always be able to find a table of those online somewhere if you ever need access to it. It just might be in a slightly different notation with what's inside the parentheses. But for us, just remember we're putting alpha to the 1/2 x in there. And then final component of our wave function is this Gaussian function here, that e to the minus alpha x squared over 2. Okay, so let's start with our psi 0. It's going to be our simplest one. So psi 0 of x, we want to just piece that together. So first of all, we want to get the value for our normalization constant. So let's find n sub 0. So here we'll just plug in our values there. This one's nice and easy. Okay, so this factorial term here, right, everything's going to go to 1 on that, so we're just going to be left with the alpha over pi to the 1/4 part of that. So there's our normalization constant. Next, we want to do that Hermite polynomial. So for n equals 0, we're going to be looking at this first Hermite polynomial in our table. So again, nice and easy. It's just a 1. There's actually no function that's going to include that alpha to the 1/2 x term. So the Hermite polynomial will just be 1. So h sub 0 of alpha to the 1/2 x, in this case, will just be 1. And then we're just going to put everything together. Okay, so psi 0 of x equals normalization constant, alpha over pi to the 1/4, times our Hermite polynomial, that's 1. And then we have our Gaussian function at the end. So the final equation for our n equals 0 harmonic oscillator wave function is alpha over pi to the 1/4 times e to the minus alpha x squared over 2. So there's our final version for psi 0. Okay, so now we're going to go through that all again for psi 1. Okay, so this time we're doing n equals 1. All right, so we want our normalization constant for n equals 1. Plug that in there. Okay, so then when we evaluate that factorial part of our equation, we're going to end up with 1 over the square root of 2 times alpha over pi to the 1/4. And then a lot of times you'll see this notation where that constant is brought inside the parentheses here. So I think if you look in Macquarie's version for this, you'll probably see it written as alpha over 4 pi to the 1/4. And those two expressions are equivalent. So here we're just bringing that square root of 2 inside our parentheses. Okay, so then we need our Hermite polynomial portion of our wave function. So let's look at that Hermite polynomial when n equals 1. So again, we want to look over at our table of Hermite polynomials here. We're going to get the n equals 1 version for this wave function. So we see that equals 2y over here. Remember, the y for us is that alpha to the 1/2 x. Okay, so we'll just put in 2 times alpha to the 1/2 x. Okay, so, and in this case, we are multiplying. So once we actually evaluate that Hermite polynomial expression here, this is now a multiplication, whereas over here, that is h of alpha to the 1/2 x. Kind of confusing, but hopefully that clarifies how we work with those Hermite polynomials. Okay, so then we just say that's 2 alpha to the 1/2 x. All right, now we just put everything together once again. So start with our normalization constant, put our Hermite polynomial in there, and then we have our, don't forget your Gaussian function at the end. Okay, so this is the expression for the n equals 1 harmonic oscillator wave function. Now, we can obviously sort of arrange this a little bit more simplified. You might see a slightly different version of that depending on where you're looking up your wave functions, but this just kind of shows you how we're piecing the different components together. So that is the function you would want to work with if you're ever using the n equals 1 harmonic oscillator wave function. Okay, so go ahead and practice maybe doing some of the higher energy wave functions. This will be good practice with using your table of Hermite polynomials. So see how you do putting together an n equals 2 wave function, and check your answer with the result in Macquarie. Macquarie should have a table that lists all of the harmonic oscillator wave functions all put together for you. Okay, so the second exercise that we're going to go through is doing some calculations with our wave functions. So here we're going to show that the psi1 for a harmonic oscillator is normalized. So again, we are just going to go through the same process that we've done before, just like we did for particle in a box, right? The normalization condition is the same for any system that we're going to look at. Okay, so we've got that integral over your bounds. In this case, the bounds for a harmonic oscillator are -infinity to infinity. And we're going to have psi star of x times psi star. Oops, it's times psi 1 of x. Okay, so psi star psi, right? And we want to show that that equals 1 for us for the harmonic oscillator wave function. Okay, so remember from our previous exercise, we've already determined our psi 1 of x, so this is what we're going to plug in to our normalization expression. Again, you could simplify this more if you want, but I'm just going to use what we had from before. Okay, so we'll have the integral of psi star Okay, so hopefully you're noticing that once again we have a situation where our wave functions are not complex for the harmonic oscillator, so there's no i's that are popping up in our wave function expression. So I'm just going to simplify this and know that we're just going to square that whole wave function. Okay, again, we can do this because we don't have a complex function, so it just simplifies our notation a little bit. Okay, so let's pull out all of our constants. So let's get our normalization constant out here. Let's get that part of our Hermite polynomial out of there and focus on exactly what we have to evaluate in our integral. So we'll just take these out front. Remember, we're squaring them, so that 1/4 becomes a 1/2, and our 2 alpha to the 1/2 becomes a 4 alpha. Okay, so be careful with that. And then we're left with x squared e to the minus alpha x squared dx inside of our integral. All right, so again, remember, all of this is squared, and that's how we end up with our x squared times e to the minus alpha x squared. Okay, so to evaluate this integral that we have here, you would look up in your table of integrals. Just so happens that the inside cover of Macquarie has a relevant integral of this form. There's just one little difference. Okay, so look at our limits here. So here we're going -infinity to infinity. The integral that's been evaluated here goes from 0 to infinity. Okay, so one neat thing about our harmonic oscillator wave functions is that they have what we call even-odd function behavior, and then that is a tool that helps us with our integral evaluations. It makes things a little bit easier. So even though our limits are different with these expressions, by recognizing that our wave function, or our function that we have in our integrand here, is an even function, allows us to say, okay, well, that's just essentially 2 times this integral from 0 to infinity. So when we evaluate that, we can just say that the result is going to be 2 times the result of evaluating this integral, where for our particular situation here, our n is going to equal 1 and our a will equal alpha to match up with what we have right here. So when you do that, so take a second and evaluate that integral, you should come up with 1/4 alpha times pi over alpha to the 1/2. Okay, but then we're going to multiply it by 2 so that we get our full coverage of our integrals. Again, that is because of our even function behavior. Okay, so in this third exercise, we're going to show that psi 0 and psi 1 for our harmonic oscillator are orthogonal. So once again, same expression as we have been using previously. Okay, so same but different. So we're going to integrate. So here our orthogonality condition is going to be psi 0 star psi 1 dx. Okay, and ideally, since these are non-degenerate eigenfunctions of the harmonic oscillator, we should get a result that says that they are orthogonal. So this integral will hopefully come out to be 0, so we'll test that. Okay, so here we have our psi 0 and psi 1 wave functions from our first exercise, and we will just plug those into our orthogonality expression. So again, we have non-complex functions, so that star is not going to be very meaningful for us in this particular exercise, but I promise someday it will be. We'll get some complex functions in there soon. Okay, so here we've just put in our psi 0 function times our psi1 function, and we're going to integrate that over our bounds. Again, negative infinity to infinity for the harmonic oscillator. So as usual, let's pull out all of our constants. Okay, so we'll just, again, you could simplify these with the alphas if you wanted to, but I'm lazy, so I'm just going to leave them like such. And then we'll see what we're left with inside of our integral. So once we pull out all of our constants, so our alpha over pi to the 1/4, our alpha over 4 pi to the 1/4, and our 2 alpha to the 1/2. Okay, pull those constants out. That leaves us with x times e to the minus alpha x squared dx. So here, remember, we've got these two Gaussian function terms. So when we multiply those together, our 2 in our denominator goes away. So we're just squaring those functions essentially. Okay, so we have an integral that we need to evaluate. So one thing that we want to take a look at first when we're working with our harmonic oscillator wave functions is to remember that we have that even and odd functionality. Okay, that's going to come in to play. So we've got a function of x. That's an odd function. We have our e to the minus alpha x squared function. That's an even function. Okay, again, if you're having trouble picturing these as even and odd functions in your head, go ahead and plot them, start to get a feel for how to recognize those. Okay, so obviously x's to the odd powers will be odd functions for us. If they're to the even powers, then they're even functions. Okay, start to get a feel for that. So what we're doing here is essentially taking the integral over an even space of an odd function. Okay, so when we do that, because remember odd times even is odd, so overall we're getting an integral of an odd function, and we know that that is equal to 0. Okay, so now you understand why I was lazy and didn't bother to do much with all of this junk over here, because I knew that this lovely item right here was going to go to 0 because we're integrating an odd function over all of our space. An even space centered at 0 is the key there. Okay, so our psi 0 and psi 1 are in fact orthogonal. Okay, so that whole expression is going to equal 0. Okay, so all right, so hopefully this has been helpful in getting you acquainted with working with our harmonic oscillator wave functions. Okay, so the keys there are remembering that your 0, your even term function, so 0, 2, 4, 6. Okay, if we look at that, we notice those are all going to be even functions. So go take a look at those. Satisfy yourself that all of the even states are in fact even functions. And then all of your odd states, okay, we get that little odd function x in there. Okay, all of the odd states are going to be odd functions. Okay, so make a little note there. So odd states are odd functions, and your even states are even functions. Okay, it's a good thing to remember for your harmonic oscillator wave functions. Oops, supposed to be an exclamation point. Yay. Okay, so that makes life easy for us when we're evaluating what at first glance will appear to be kind of a nasty integral, but we can simplify life with our even and odd functions quite nicely, and not have to do too much in the way of evaluating. Okay, so hope that was helpful, and I'll see you in the next video.